please. Hello, everyone, and welcome to the final Faster webinar of this series. And we've saved the best till last, arguably. We're discussing the ethics of electric vehicles, everything from raw material extraction right the way through to recycling. And we have a star-studded cast for you today. So I will let one by one the panelists turn on their cameras and wave hi. We have Lucy Crane from Cornish Lithium, who are doing incredible things with UK-based lithium extraction. We have Fergal Harrington Beatty from Amte Power, a British cell manufacturer with technically a Scottish cell manufacturer, because their factory is based up in Thurso at the moment, but they have very big ambitions. So good morning, Fergal. Professor Emma Kendrick, University of Birmingham, who is definitely in the top tier of battery academics in the UK at the moment, doing incredible work with recycling and also with a font of knowledge when it comes to cell chemistries as well. And also my former colleague from WMG back in the day. And finally, Graeme Cooper, who is the grid guru from Jacobs. What he doesn't know about basically your transmission and distribution grids isn't worth knowing. And I know he's certainly a very popular panelist on the show today. So in that case, before we launch into proceedings, we might as well have the first poll of the day, just to find out who we've got with us today, really. So Donald, if you want to stick up the poll, please. So yeah, are you an EV driver, prospective EV driver, no plans to drive an EV? Are you from the EV supply chain? Are you a retailer, et cetera, et cetera? Yeah, let us know who you are, what kind of sector you're from, or you know, basically what your particular interest is in today. So we shall just let you vote on that, and then we'll display the results to see who we've got. It's always interesting to see who's intrigued by what we've got at the moment. Good morning to everyone in the chat who's saying hi. There's so many of you who've come through from, yeah, quite a good Scottish contingency as well, including Dorothy from the Isle of Skye there. That's great, very much part of the Faster Project regions. In fact, I believe you're getting at least one Faster Project rapid charger on Skye to add to your recent additions that there have been since my road trip there a few years ago. So in that case, can we display the results, Donald? Oh, there we go. So mostly, about half of you, existing EV drivers, and then you've got, you know, coming up on a fifth who are considering it. And hopefully today's webinar will help to allay any concerns that you have. We've got fleet managers. We've got, that was transport managers as well. I'm surprised I didn't put that in the tick box options. That was a bit of an oversight from me. So yeah, there we go. Fleet managers obviously interested in the carbon impact and the ethical impact of their EVs. So excellent. In that case, we'll launch straight into things. If we can bring on Emma and Fergal for this one, and we can talk chemistry for a bit. So what's in a lithium-ion battery? If we were to get the typical shopping list, Emma, of course, you've spent so many years studying cell chemistry, so we'll start off with yourself then. What's the typical shopping list for a lithium-ion cell?
Well, a lithium-ion battery is typically made of a negative electrode, a positive electrode, and it's separated with a separator, an electrolyte. So in the positive electrode, we have a cathode. This is typically a mixed metal oxide, which contains lithium, nickel, manganese, cobalt, or iron. And it's then mixed with a binder and a conductive additive, and then coated onto a current collector, which is aluminium. And on the negative side, we typically have a graphite, which is treated in the same way. It's mixed with a conductive additive, carbon black, typically a binder, polymetric binder to stick everything together, and it gets coated onto a copper current collector. And then in the middle, we have an electrolyte, which is an organic electrolyte of carbonates with a salt in there, which is lithium hexafluorophosphate, LiPF6. And this is all then stacked or wound and contained within either a pouch cell or a can or a prismatic can.
In fact, yeah, something similar to this. We'll see if it's going to blur it out. Yeah, I thought it might happen because of the virtual background. But if I put it in front of my face, here's one I made earlier. Well, I didn't make it.
18650.
18650. There we go. Spot the pro. That's the point. So Fergal, you are a company that has built Is it
We are.
1850s or is it 2170s, which is the slightly bigger version that you're working on as well?
Yeah, 2170s. So I think as everyone knows, that's the way the market is moving, sort of cylindrical cell wise. So that's the cell format we make at the Amte in our Thurso facility, and also that we've made at the UK BIC in Coventry.
Oh yeah, the UK Battery Industrialization Centre. So that's kind of the it's not a big gigafactory like Tesla size, but it's basically a battery factory for hire, isn't it? In terms of helping to develop the latest chemistries in academia and industry. So you're doing pouch cells as well, aren't you?
Yeah, we are. So the chemistry we use is a NCA chemistry, so that uses nickel, cobalt, and aluminium. And we are talking about the greenness of batteries. We're aiming to maximize the nickel content of our cells to reduce the cobalt, because generally there's a higher CO2 and environmental and ethical cost associated with cobalt versus nickel. So hence that's the way we're going.
But it's interesting you mentioned that, because cobalt's already quite a small percentage of NCA, isn't it? It's a tiny fraction versus the nickel that's in there. And I mean, you compare that to the original lithium-ion cell, which was lithium cobalt oxide, wasn't it? And that was about 39% cobalt in the cathode, the positive electrode. NCA, you're probably nearer, what, 3% cobalt, maybe thereabouts?
Yeah, I wouldn't know off the top of my head for our particular chemistry, but it's certainly very low. And yeah, it's in there for I think, as everyone knows, the thermal management of the cells, so to make it more thermally stable. Also, by increasing the nickel content, we're able to get to higher levels of sort of energy and power performance. So not only is there sort of a sustainable driver for doing so, but also a performance one.
True. And actually, well, obviously we're discussing the elimination of contentious materials, and we'll go on to those contentious materials in more detail. But crucially, one thing that we keep hearing is that lithium-ion batteries have allegedly got rare earth elements in them. Is there any truth to this?
When they say rare earth, normally we think of things like lanthanides and actinides. Now, if you're talking about an electric vehicle, then yes, lanthanides are in an electric vehicle because they're used for motors. And so there are lots of small motors all the way through an electric vehicle which power even things like speakers, for example. So they're contained within the electric vehicle, but not within a battery.
And of course, if you're using an AC induction motor, which Tesla uses in some of their models, and I think the Renault Zoe uses it too, then that means you've not got permanent magnets, which means that the actual powertrain, the battery right through to the motor, doesn't use rare earths. Would that be correct?
It is, but I think there is a general move towards, as I understand it, away from induction towards permanent magnet motors, and that's just because of the magnet, it gives them an inherent sort of torque advantage, so it actually creates a more efficient vehicle. I know they are also looking, of course, to reduce rare earth metal usage within the motors themselves. I know that's a big industry topic at the moment.
True.
And also recycling of those rare earth magnets as well, to create a better circular economy, because most of the rare earths, I believe, currently come from China. True.
Exactly. So that CO2 footprint, I think, of both electric motor and battery, I think, are two of the key things when looking at an electric vehicle in terms of its sort of green credentials, sort of inverted commas.
Which kind of brings us to kind of the topic of critical materials. So we mentioned the lanthanides, neodymium, for example, which is used in the magnets, is a very critical material. And the critical materials are assessed within different regions of the world. So Europe has its own critical material list. As of last year, the UK now has its own critical materials list as well. And this list is based upon security of supply and of economic importance to the region. So a lot of the materials in lithium-ion batteries are critical, not just because they're used in batteries, but because they're used in other industries as well. So we have lithium, which is on the critical materials list for Europe and the UK, cobalt, and also graphite. So a lot of the raw materials that are used in lithium batteries are of high economic importance, and there is a supply chain risk for them. So we do need to consider where they're sourced from, whether we can create a better circular economy in the UK for these materials, and Europe, of course, and also the ethics of where they come from too.
Yeah, and it's a highly, I think, complex consideration, because obviously you have a cost component, and then you also have a CO2 component of those materials, and the ability of the cell chemistries themselves to be recycled. So of course, the higher proportion of valuable materials you have within a battery cell chemistry, the more compelling business case you have for a recycling supply chain to form around it, and the more sort of natural business incentive. Of course, that's when then government incentives and legislation becomes really important, to where the business case is lacking for other chemistries, perhaps that needs to come in and incentivize sort of businesses to take on that responsibility.
Now, you raise a good point on recycling, and we will cover this in detail later, not least because Emma's work has been exceptional in that regard. There's some very exciting progress that's been made at the ReLib project. But in terms of lithium ion, well, not basically beyond conventional lithium ion, what chemistries are coming up that are moving away from some of the controversial materials that we've mentioned today? So certainly, Emma, I know that you've previously dabbled in some of these chemistries before, but if we start, for example, with lithium sulfur, which has been something of a bittersweet UK success story in a way, but does seem to hold a certain amount of promise. Tell us more.
I mean, lithium sulfur is an interesting chemistry because you're using sulfur as the positive electrode, so it's very abundant, it's very cheap, it's very light, and then it's manufactured in a very similar way to lithium ion. But on the negative side, instead of using a graphite, you use a lithium metal foil or something similar to that instead. And it does offer some interesting high energy densities. And if you're looking at incorporating, say, a new technology into aerospace, for example, then the watt hours per kilogram for aerospace is really important. And lithium sulfur offers kind of a 500 watt hours per kilogram, which is kind of a magic number that people are trying to work towards. It does have its limitations. As with any chemistry, there are problems that need to, or opportunities that need to be investigated to prolong the lifetime a little more. And in lithium sulfur systems, we have what's called the polysulfide shuttle. So we start to dissolve some of the products that are formed in the cathode. As the cathode gets lithiated, they're slightly soluble, they dissolve into the electrolyte, and they can shuttle back to the negative electrode and kind of pacify the surface of the lithium, but also that results in an energy loss associated with that as well, and leads to degradation and short lifetimes. So there's some challenges associated with it, but there are also some opportunities. The one thing that has not been yet addressed is the volumetric energy density actually isn't that great. But in terms of gravimetric, it does offer some pretty good opportunities there.
So just to kind of clarify for anyone who's not from an electrochemist background, so the gravimetric, your watt hours per kilogram, basically how much range can you squeeze into a given weight, and then volumetric, as you said, how much range could you squeeze within the constrained kind of space you would have within a vehicle to actually put those batteries. And that's why, yeah, you could have a very light battery, but it might not give you a huge amount of range. Although that said, the lightness of the battery means that you would get a little bit more range than an equivalent capacity of conventional lithium ion, because the vehicle's lighter, so it needs less energy to move a certain distance, I suppose. But no, it's a very promising thing, isn't it? Another interesting chemistry, which Amte is working on, of course, goes beyond lithium entirely. So you've got your sodium ion under development, don't you, Fergal?
Yeah, we do. So that's a really exciting chemistry for a number of reasons. I would say number one is obviously it uses zero lithium. So from a raw material sustainability supply chain standpoint, that we're actually in the process of quantifying exactly how much CO2 that does save compared to a LFP equivalent cell. So we're working with an ESG consultancy to do that, to help us track that CO2 throughout the supply chain. We know it's going to be less, but we really want the sort of the hard figures to say exactly how much. So with sodium, there are a number of chemistries. I would say the leading two that are being considered are multi-layer oxides and Prussian blue analogues. So almost like the LFP and NMC of sodium, I would say, is a way to think about it. We are looking at a sodium nickelate chemistry, so still using nickel, but by removing that lithium, there's a significant sort of CO2 saving. Not only because of how lithium is mined and then refined, so obviously there's a high energy cost to that, but also the global supply chain at present for lithium is obviously dotted all over the globe. So there are significant sort of shipping emissions in between those very high energy stations as well, which is something to think about when considering sort of the greenness of the chemistry. Sodium also, you can use existing sodium resources. So you can use rock salt mining or evaporation that already exists and they are much more distributed rather than the sort of lithium hotspots we have around the globe at present. And also that means less sort of CO2 in terms of shipping those materials. So potentially a lot of countries could make sodium sort of in country, and the whole supply chain could be there, at least from a sodium perspective. So I think that's going to be really compelling. Also from a shipping point of view, there is sodium can be shipped more efficiently because it can be shipped at 0 volts. So that's a unique component of the chemistry, which would just potentially mean that it can be, reduce CO2 again in that element.
So a couple of interesting points there, just for anyone again who's not from an electrochemist background. Shipping at 0 volts, if you were to take a conventional lithium-ion cell like this one and then discharge it so it was completely flat, you'd basically have irreversibly damaged it. It wouldn't be safe to recharge it. So when an electric vehicle's battery is flat, it's actually still got a fair chunk of voltage in it. It just can't go below that voltage, otherwise it risks being damaged. Whereas you could literally short out these terminals and you could put a resistor across it, ship it across the world with no energy in it, and then recharge it and it would be fine. And that means that you don't have that risk of anything going horribly wrong because of residual energy within it. And then the other couple of things you mentioned that might confuse people, LFP, lithium iron phosphate, and then NMC, lithium nickel manganese cobalt oxide. NMC is the most commonly used in electric vehicles. It's the one that's got a little bit of cobalt, mostly nickel, but LFP is actually another one which, due to time constraints, we can't really go into too much detail, but it's a mature chemistry that's been used in the standard range Tesla Model 3 and Model Y, in the standard range MG4, and in some electric vans, and it's been used in electric buses for yonks now. No nickel, no cobalt, it's safer, it's more ethical, it's longer lasting, doesn't like cold weather very much, but if you've got a decent thermal management system within the battery, like Tesla does, it kind of strategically heats it, then you can still get decent range out of it in winter. And basically you've removed the ethical concerns with the positive electrode, well, by and large, in comparison to NMC. And actually, anyone who goes on to Twitter to complain about EVs being bad because they use cobalt, there's less cobalt in an LFP electric car than there is in the smartphone they used to tweet that. That's quite a nice little. Also, petrol and diesel require cobalt to refine. So anyone driving an LFP equipped electric car is using less cobalt than anyone driving a petrol or diesel car. So that's two key rebuttals for anyone who goes for the low-hanging fruit in terms of criticisms. I'm aware due to time constraints, we will have to kind of scuttle on here, but lithium, of course, got mentioned in terms of kind of ethical concerns around extraction, and Lucy is the perfect person to bring in just now from Cornish Lithium. So Lucy, if we kind of start by discussing how lithium's typically produced today and what the ethical concerns of that are.
Yeah, absolutely. So at the moment, as Fergal said, current supply chains for all of these raw materials are global. And in the UK, we currently have to import absolutely everything. Emma mentioned the critical minerals strategy that the UK government produced in July last year. And that's the first time we started to think seriously about how we're going to create our own reliable supply chains of these critical raw materials. And some of that requires looking closer to home and what we've got on our doorstep, but also working internationally with partners. So at the moment, most of the world's lithium either comes from a hard rock, traditional quarry in West Australia, or it comes from these salar type deposits in South America. So you might have seen photos of big evaporation ponds that span kilometers and kilometers. And what they do is they pump up really salty brines that form anywhere down to about 200 meters below the surface, pump them into these big evaporation ponds, leave them for 18 months or 2 years, and as the sun evaporates off the water, they get saltier and saltier, and then they can process that mineral concentrate into a lithium carbonate product, for example. More often than not, the lithium that's produced from hard rock in West Australia or the lithium that's produced from these salar type deposits in South America will be kind of refined up to a certain stage, and historically it's then been shipped over to China because they've been very smart at seeing this energy revolution that's happening and have developed most of the world's capacity to refine these battery materials into kind of battery grade products. And rather than just necessarily producing a battery grade lithium hydroxide, for example, they'll perhaps also produce your battery cells and your battery packs, and would ideally put them into an electric car and then sell that. So I think the UK see it as a huge opportunity, and lots of other countries around the world, if we can gain some of that value chain, domestically, then that could have real benefits.
And on that note, of course, Cornish Lithium is a UK company that's doing things a little bit differently when it comes to lithium extraction. Tell us more about the technology, the improvements over the standard procedures today, and then when we could hopefully see that in commercial operation. Yeah, so we're exploring for lithium down here in Cornwall, and we've got lithium in 2 different sources. So one of it, so the whole of southwest England, and tell me if I go into too much of a geology lesson, is underlain by a big mass of lithium enriched granite. And there are certain pockets of that granite that are more enriched in lithium than others. So in the centre of Cornwall, near St Austell, there's been china clay extraction happening from big open pits for nearly 300 years. And it happens to be that the kind of western flank of that St Austell granite is a high lithium granite. So we've known about it since the 1980s, but there wasn't really much lithium demand there. Whereas fast forward now, it's interesting to see what we've got on our doorstep. So one of our projects is looking to repurpose an old china clay mine. It's already an open pit. We just want to push it out and go a little bit deeper. And we're looking to use a new technology that's been developed by an Australian group called Lipidico, which allows you to extract the lithium and produce a battery grade lithium hydroxide product on site. So cutting out that having to ship it to somewhere else to be refined, secondary refining. And that's really exciting. And it's a hydrometallurgical process rather than a pyrometallurgical process. So basically, we're not going to have to heat the rocks up to nearly 1,000 degrees Celsius, which is what happens in a lot of these processing routes. And then the second work stream that we've got, which is potentially the really exciting one, is there's actually lithium contained within geothermal waters. So these are deep groundwaters that circulate naturally in Cornwall. I said that the whole of Cornwall is underlain by this big mass of granite. And if you think of a granite work surface, it's not permeable. And that's why these geological faults, these fractures, cracks in the rock are so important, because that's where there's space for these deep groundwaters to circulate at depth. And basically, because they've been flowing through lithium-enriched rock for a very long time, they've become slightly enriched in lithium. So we can put boreholes from the surface, drill down to about 2 kilometers, pump these waters up to the top, and we're using a type of technology called direct lithium extraction, which is either like a ion exchange mechanism or a highly selective membrane. You can just remove your lithium ions from the water, recover that as lithium chloride, and then our idea is that we will re-inject that lithium depleted water back down into the geological system. But what's also exciting about it is that these waters will be about 70 to 80 degrees Celsius. So we're looking at partnering, well, potentially using some of that heat in our own process, but also partnering with local businesses who want to decarbonise. So a bit different to how people might think of mining. That is incredible. So it's potentially self-sufficient in terms of that geothermal powering that you've just mentioned. And
Potentially.
yeah, well, we go some way towards it at the very
Absolutely.
least.
Yeah, very different to these current global supply chains. Absolutely.
Yeah. And in terms of freshwater use for direct lithium extraction, is there any freshwater input at all? So it's literally sort of self-contained. So looking at these salars, these big salt lakes that you just referred to, that's the kind of the standard today. That direct lithium extraction technique could solve drought issues. Well, I mean, if an area is drought prone, it won't solve the drought, but it will solve.
Can have a really positive impact on minimizing those environmental impacts that are currently there.
Exactly. You're not tapering off water or siphoning off water for an industrial process, whereas it should be used for obviously drinking and crops and so on. So that is hugely beneficial. So this is not just something that would scale well within the UK, but globally. And Absolutely. Of course, you're not reliant on sunshine for the evaporation.
No, yeah, because down here in Cornwall, it is actually sunny today, but no, we can't rely on sunshine for our process.
So actually, I suppose that's part of the reason why, despite the, shall we say, challenges to UK industry since certain mid-2010 events, there's still talk of battery factories being built because we've actually got really good raw material supply right on our doorstep. So when do we expect Cornish Lithium's mine and brine-based lithium to be commercialised then? What sort of time frame are we looking at?
I'd say 3 to 5 years. So we're kind of on the cusp of it now. I think globally in the mining industry, once you've actually found a mineral deposit, which is not necessarily easy, it's then taking 16 years to bring a mine on stream. So, Cornish Lithium was founded in 2016, and we've now found some lithium deposits. So we're trying to compress that timeline, but crucially, we've got really high environmental standards here in the UK. We've got to treat our workers fairly, and it seems a really compelling argument for trying to do this in the best possible way.
Yeah, that's brilliant. I mean, I knew some of what Cornish Lithium was up to, but you've really just kind of hit the nail on the head on just how valuable this is. And in terms of that commercialization, something tells me that you and Fergal will have already had chats by now, but it's a no-brainer to obviously localize the supply chain as much as possible. And indeed, Emma, for new cell chemistry development, you'll need that raw feedstock. But that said, of course, you'll be able to get that feedstock from your own recycling projects that we'll come on to later. And when you mentioned, Lucy, pyro and hydrometallurgical techniques, I just knew that the kind of inner school child in Emma was like, oh, me, I know those terms, because obviously that goes into the recycling side of things too. Now, obviously, we have our resident lithium expert, Lucy. When it comes to cobalt and nickel and the extraction involved in those, I don't want to necessarily put people under the spotlight. Does anyone feel confident to discuss the ethics around those? Because I've got some information, but I don't want it to be like, the Euan show. I'd rather that everybody got a chance. Any volunteers on cobalt, first and foremost?
I can talk a little bit about it. I think most people are aware that the vast majority of the world's cobalt is sourced from the Democratic Republic of Congo, which has challenges around how democratic it is, but also potentially, there's a really big artisanal mining force, I suppose. And a lot of these artisanal miners are not paid very much at all, and they might be school children or school-age children, and working conditions are often very unsafe. There's no health and safety, and some of the processes they use to kind of refine the cobalt initially are dangerous. They're exposing themselves to chemicals and things that can give them problems later on in life. It's a really difficult one because it's very hard to say black and white, oh, well, in that case, we need to stop buying cobalt from artisanal miners, because actually that might be their only source of income and the way that they're providing for their family. And so I think there needs to be a much broader conversation around how can we support artisanal miners and put a framework in place that actually there are health and safety standards that people are adhering to, and we're actually paying these workers a fair wage. So just saying, oh, we can't source cobalt from the DRC is actually, in my view, not perhaps the best answer. And I had a really interesting nickel statistic the other day. So I think a lot of nickel is produced in a very energy intensive way. Fergal mentioned the huge carbon impacts that are associated with this. And I also heard a stat that apparently the average nickel atom travels 3 times around the globe before it makes it into an electric vehicle, because of how far it has to travel from mine to refinery to everything. So, you know, at the moment, these supply chains are so global, and that really has an impact on what the overall impact of us actually producing these vehicles is. So there's a real,
Yeah, I mean, you've raised some great points there, particularly if we go back to cobalt very quickly on the artisanal mining side of things. So yeah, even in Democratic Republic of Congo, most of it is big open cast mines that are owned by the mining giants, and everything's done to the letter in terms of safety, etc. But artisanal mines, as you say, you know, they actually do have an economic value for very deprived areas. Of course, kids should be in school, not in mines, and that needs to be addressed, as does the safety and the wages involved. And what we saw towards the end of the 2010s was that there was a bit of a stampede away from DRC towards Australia, etc., by the big companies, you know, the kind of Panasonics and Teslas and LG Chems of the world. But there was one little Dutch company, and I might actually have one of their products sitting next to me if the camera's not going to, there we go, you can just about make it out. Fairphone came running straight into DRC and said, we want to help. And they set up living wages, they set up making sure that kids were in school, set up safe practice, etc. And now there is the Fair Cobalt Alliance that a lot of these big cell manufacturers and EV manufacturers are signed up to, so that something is actively being done about this. Do you see the BPs and the Shells of the world signed up to the Fair Cobalt Alliance? I don't. The last time I checked, I didn't see any of their names there. They're still using cobalt as a catalyst to refine petrol and diesel. And then the people who drive those cars are the ones that tend to complain about the cobalt use despite the fact that they're giving petrol and diesel cars a free ride. So yeah, maybe look at who's a member of the Fair Cobalt Alliance before making those judgments. The other thing as well is it's used in jet engine alloys as cobalt. So try not flying if you can. But also nickel. Yes, it is quite carbon intensive to produce, but that's because it's energy intensive to produce. But that doesn't necessarily need to be energy from carbon intensive sources. And there's a company called VKTR that is planning a renewably powered lithium refinery in Indonesia, which has a very carbon intensive grid. So they're basically creating an island of renewable energy in a sea of fossil fuels. And that's something that could be done by any heavy industry anywhere. It doesn't need to be anything to do with batteries or electric cars. If you have a massive factory with loads of roof space, plaster it with solar panels, got some room for some wind turbines, stick them there as well. Guess what? That will reduce your energy bills as well as your carbon footprint. And moving on to that, it's time to come back to yourself, Fergal, about the energy intensiveness of running a lithium-ion battery factory. So, you know, how carbon intensive, how energy intensive is it, and what are the most intensive processes? What's the thing that's using the most energy in a lithium-ion factory?
Yeah, so in the cell manufacturing process, to break it down at a high level, there is what we call a wet side and a dry side. So the wet side involves the mixing, coating, and calendaring. And without getting too into the detail, that's effectively taking the material you want to put in the battery, mixing it in a big mixer. Imagine like a food factory, a bakery. Actually, some very similar mixing equipment has transferred over into the cell manufacturing industry. And then that is then layered on the electrode foils and effectively sandwiched together. If you imagine a cake, we tend to use a lot of baking analogies in the cell manufacturing space because of those similarities. So that process is intensive in terms of that's quite large scale manufacturing equipment. But I wouldn't say there's anything particularly special there to cell manufacturing. You see that equipment across the board. So that has, and the reason that's important, it means it's been quite optimized already. So a lot of that equipment is as energy efficient as you can get it. But of course, there's an energy cost associated. I would say that the main energy intensive process in the cell manufacturing process, and it's so energy intensive, it actually defines where cell manufacturers go and set up, is in the dry room side of things. So part of the cell manufacturing process requires a lot of energy to maintain a very hot and dry environment. And that is why you see major large-scale cell manufacturers such as Tesla's venture with Panasonic setting up in the most hot and dry environments possible. So imagine Arizona, Nevada. So a lot of people don't realize the reason they're out there, not only because of the incentives that were available and political reasons, but also because from a purely energy point of view, the closer you already are to that hot and dry environment, the less energy you have to spend trying to get there. Hence that reason. So for us, that's a big focus for us, is getting the most efficient dry room environment possible. You can optimize that in your cell manufacturing process, so minimize the time in the dry room. That's one way to achieve it. So effectively you have to have that dry room on for less time, but also using the best equipment possible. So at Amte, we're constantly looking at sort of the next generation cell manufacturing techniques across the board, including the most energy efficient dry rooms. So that's how we view it, I think, on our side. The final thing worth mentioning, just because it is also energy intensive, is the formation and testing process. So that's the final stage of the cell manufacturing process, where the cells are run through a number of cycles. So effectively they're charged and discharged, and that's what happens at the end of the process before we can then ship those cells to customers. And that's where the cell sort of becomes the cell, really. It's the final stage of the process. So also there, by making sure we try and use the shortest formation and testing process possible to deliver a safe and reliable battery cell, we can again then remove energy usage from that process and reduce the CO2 overhead of the cell. So I'd say the key takeaways are optimizing the dry room and optimizing the formation and testing, and you will have the most efficient cell manufacturing process possible.
True. And I honestly had no idea that that's why Tesla set up in Nevada. And
part of the reason, certainly.
That is genius. That is so clever. I mean, that said, of course, there's a lot of cell manufacturers now setting up in places like Norway and Sweden. And of course, UK BIC is in Coventry. I remember when I was at WMG, which is also Coventry, spending an hour in their dry room for the first time, and then coming back out on what was a very typical West Midlands high humidity day, and just kind of breathing in all of this moisture that's clearly been through like half a dozen other people before me, and just thinking, oh, nature is horrible, I don't like this world anymore. It was genuinely distressing. But yeah,
I can relate to that.
Yeah, it's just that it was such a shock to discover just how, like, you know, moist the atmosphere is. And of course that is what's removed in a dry room. But
exactly,
one of the key developments as well, which I've been reading, can lop about half of the energy costs off of a lithium ion cell production, is dry electrode coating. So Emma, is this something that you've got experience with in your research, dry electrode coating, and the kind of progress that's been made?
We have a little bit. I mean, our focus here in manufacturing is to try and reduce the environmental and the cost impacts. So we've been looking at reducing solvent content. You can reduce the solvent content quite a bit, which then reduces the energy that you need to then dry off the solvent during the drying process as well. And if you can remove that solvent fully, then there's no drying process required at all. If you do remove the solvent completely, then you actually have to use a slightly different type of mixing process at the front end, which is more of a high intensity mixer. So again, there's a bit of a trade-off there in terms of the energy inputs around that processing. And quite often you use a slightly different binder as well. You would use a PTFE binder, which is Teflon, which you can put on pans, rather than the PVDF, which is a similar polymer, but it's just got one less fluorine in it. And you would jet mill that, or you would mill that really high intensity, and the polymer starts to fibrillate. So you start to get this web of polymer that all of the materials then stick into. So it encapsulates everything. And then you pour it onto your current collector, and you can hot press it into a porous electrode without the solvent being there. Obviously, there's careful control that you need for depositing that powder to make sure you've got an even coating as you go through, and then you have to repeat it the other side for the double-sided coating that you use in the batteries as well.
Yeah, but fundamentally, it sounds like you're requiring a lot less heat to dry off solvent, because there is no solvent now. So yeah, I mean, that's basically where you're saving so much cost, because ovens are expensive to run. So is, you know, a dry room, anything that's removing humidity, but the ovens are by far the biggest part of the energy bill. And of course, if you're building a gigafactory somewhere that has a predominantly fossil fueled grid, that's where the carbon intensity of the battery comes in. But if you're powering it with solar panels, etc., then in theory, yes, it could still be a high energy bill, but it could be very clean batteries. And that's interesting.
I think it's also time related in a way.
True.
So in the large manufacturing sites, you have meters and meters of drying area. So that's a land cost as well. So if you can actually reduce that down, you reduce the land cost that's needed for the manufacturing as well. Which comes to your...
Sorry, I was going to say, it's certainly on our roadmap, dry electrocoating. So currently we use the wet process because that is the one accommodated by the majority of the industry. It's the one that it's scaled around, but the dry electrode process is, it's certainly something we're aware of. And I think a lot of cell manufacturers are keen to adopt. Also on NMP, which is used in the wet electrolyte, it is it's not a pleasant material, I think, to say the least. So removing that from the process also, I think we talk a lot about the ethics of cell manufacturing on a very macro level, but on a micro level, it's safer for the staff actually working on the line as well. You can remove, and for the environment around it, if you can remove these more hazardous materials like NMP. So yeah, that's something we're looking to do.
Definitely. And well, actually, talking again about the kind of on-site renewable side of things, I believe that the upcoming mega factory for Amte Power is going to take, going to make good use of that. You're going to be in sunny Dundee, where there's on-site wind turbines and kind of waste to energy and so on, isn't there?
Yeah, that's right. So it's currently our preferred site for our mega factory, and also by deploying in a site that already exists. So it's the ex-Michelin tire factory. There's also a big saving on the CO2 overhead of actually building and breaking ground in site. We know a lot of battery startups famously have sort of broken ground and not made it any further. But if you have an existing battery facility that you can sort of tap into, or existing production facility, it makes it a lot easier and more efficient to deploy, and also reduces the impact on the environment. If we can reuse existing industrial sites, then that is obviously much preferable to having to take up new land and affecting the environment and spending more CO2 there.
Definitely. Just to quickly blast through 3 points that have been raised in the comments. Lewis Standing asks, is British Volt being rescued? Yes, they've been bought out by Recharge Industries, I think they're called, in Australia. So, you know, they're now Australian owned, but they're looking to build the Blythe Gigafactory. But Amte, of course, is well, Scottish UK now. Because that's the point. You've now got kind of the Coventry / West Midlands operations kind of nerve center, if you wish, but Thurso is the original factory, and then it will be Dundee from the sounds of it, and then potentially definitely something even bigger once that's up and running too.
So our distribution is Thurso sort of pilot manufacturing HQ, Oxford R&D and project management, and London sort of sales and commercial. We do work through the UK BIC. They've been a really key partner for us in Coventry, and then Dundee is our preferred mega factory site, as you said, Euan.
Perfect. I've just seen conveniently Nigel Morris has reposted the comment I was going to try and bring up about nickel, which was the Altilium Group's Queensland Specific Minerals. Basically, they've got new nickel laterite sites in Australia, which, if it's the same ones that I had in my notes, in fact, it is actually Queensland. Yeah, it is brilliant. Okay, so you're looking at nickel and cobalt, very high yield, and it's a reduced waste with no requirement of a tailings dam. So pretty ethical as far as nickel goes with your cobalt byproduct. Cobalt does tend to be a byproduct of nickel or copper mining, to the best of my knowledge. And I think there might have been a final one that was, oh yeah, of course, Lucy. I knew there was a reason your name came to mind. You've just mentioned that there's a lot of floating offshore wind capacity due to be coming to the southwest of England in 2030. So it looks like Cornish Lithium's already earmarked a few megawatts for their scaled up operation. But I'm aware, of course, that we are kind of motoring on through, still a fair bit to get through. So we better bring in Graeme. If you can switch on your camera and your mic. There we go. Hello, Graeme. Oh, goodness me, you've got a very green backdrop now.
Well, I decided it looks like I'm going to be in the jungle, right? So I've just relocated from an open plan office. So anyway, I hope you can hear me all right.
Yeah, perfect. So in terms of driving an EV, what are the typical carbon emissions of an electric vehicle that's fueled off of the national grid today versus a typical petrol or diesel car?
Oh, so this is a really good one to pick apart because it's very difficult to nail down a figure. So I'm not going to do the politician thing and just fluff through it, but I can't give you a number, but I'll explain why. So, crikey. So let's just go back a little bit. The UK's grid, since the start of the sort of industrial revolution, right, or it's later than that, has always been driven by thermal power generation, which is obviously dirty. But when we got to about 2016, 2017, actually we got to a point where more power was made from clean sources than by burning stuff. And when I say clean sources, I'm going to do clean generation. So I'm including nuclear in that, if anybody wants to start picking apart the whys and wherefores, right? So what we see is more power being generated across the year from clean sources than by burning stuff. But as I'm sure you'll appreciate, what you find is the carbon intensity shifts hugely. So the energy market is settled in half hours, so we get half-hour granularity of use, and you can find that the grid is very, very clean on you. I guess if people want to think about this in off-peak times, and not as clean at peak times, which is why we have things like time of use tariffs, economy 7 or economy 10, those sort of types of concepts, right? So using the power when it's cleaner and cheaper. So this is where I get a little bit narked when somebody does some back of fag packet sums that says, an EV made in China, charged in the UK at dirtiest time is really bad. So yeah, let's take away the manufacture of it. In use, the nice thing about EV charging is with smart tariffs, with smart charging, you can actually defer your charging to when the grid is cleanest and cheapest. And by doing that, you actually take huge bites out of the carbon intensity of the power for each mile that you drive. But what you're also doing is you're creating a really great opportunity to help renewables, because as you'll appreciate, when people switch stuff off and go to bed and the wind's still blowing, the price of energy, renewable energy, starts to collapse. It's very difficult to finance new renewables when the thing that you make is worth less. So actually shifting time of use means that you're putting cleaner electrons in the car, and you're conversely creating up that sort of symbiotic relationship to actually help support the growth in further renewables. So it's a really difficult one to answer. So I know it's a really long answer to a really short question, but it's all about exactly when do you charge your car and the grid intensity. So I can share the carbon intensity in the chat. I put the link to carbonintensity.org. So if you look at some of the latest and smartest car chargers, they are using a couple of APIs which are really quite important. So these are the that digital signal, right? So if you're an Octopus customer, you put in your tariff you're on, and your smart charging device will look to the API for the tariff you're on. But what it's also looking at is the national grid and the carbon intensity API on how dirty the grid is now, both nationally and regionally, but also then how clean is it going to get, or how dirty is it going to get, because it gives you then a 2-day forecast. So actually wrapping this up into trying to bring it to some sort of conclusion is, that most people drive roughly, typically 37 miles a day is the average first car use a day. A lot of cars now 100, 200 mile range. So you don't need to charge your car every 2 or 3 days. So if you charge it when it's cleanest and cheapest, actually you can charge as almost guilt-free as you want. But it does rely on a few of those things coming together. Link a little bit to Lucy's comment. Yeah, offshore wind off the east, off the west coast of Cornwall. Yes, I'd hazard a guess that it probably won't be by 2030, but in the early 30s. Having been a wind farmer, kind of there, the times lag a little bit. So absolutely, another one why the location of British Volt was really quite critical. It's actually where offshore wind is landing, right, from some of this growth in offshore wind. So put it where the grid is cleanest. Dundee, I mean, the cleanest part of the UK grid is Scotland because of all the onshore wind and then growth in offshore wind. So, you're actually putting these sort of energy intensives where the grid is cleanest and then therefore likely to be cheapest.
On behalf of Scotland, I would just like to say you're welcome. as far as the cleanest part of the UK grid. But yeah, you raise a really good point about the time shifting of charging to overnight, when funnily enough, you're going to be sleeping and you just need your car to be charged in the morning anyway. So with that in mind, is it fair to say that EVs are actually reducing, well, they could actually help the grid rather than hinder it, because you're not adding to the kind of peak time load that people seem to think that they will be doing?
So when people say, does it help the grid? It's like, well, let's just unpack that a little bit, right? So when people think about the grid, are they thinking about energy, the power? Are they thinking about the wires? Are they thinking about the carbon intensity? What is it we're helping? So let's pick up a few of those things, because actually there's a multitude of benefits. So all of us, whether we know it or not, are paying for the UK's grid networks. So your standing charge, as well as doing some of the green subsidy bits and pieces, that's also paying for your networks. So to give you, I can give you grid numbers because I've just left National Grid. So National Grid is roughly, on a typical average dual fuel energy bill, about £20 a year, right, for one of the most reliable energy grids in the world. So I think that's pretty good value, and I don't even work for National Grid anymore, right? But what we're going to see between now and about 2045, 2050 is the UK will consume at least twice the amount of electricity than we do today. To be able to do that, we will need at least 4 times the amount of clean generation. And to be able to do that, you need at least twice the grid capacity, and we're all going to have to pay for that grid. So if you put cars on the grid and you charge them at peak time, you need to add more grid. So you're adding cost for the wires, both at transmission and distribution. You're adding the need for more demand. So you're adding market costs, the cost of making power and supplying that. And therefore, most of that is being met by, that marginal cost is met by dirty fuel, often gas. So when you say, well, do EVs cause a problem to the grid? Well, hypothetically they do, because it's more demand, but we know it's coming. They actually help the grid in multitude of ways. They help avoid some of the grid cost, right? So better sweating the grid asset means you're building less. You're also helping the market, because what you're doing is you're cutting off some of the potential peak and higher peak and dropping it into a trough. So what you're then actually getting is a more efficient market that's not lurching between high demand, low demand, high price, low price, high carbon, low carbon. So when you say, so again, I'm trying to add a lot more to do EVs help the grid? Yes, but they help that in a variety of lenses, whichever way you want to look at it.
Yeah, I suppose there's also the avoiding of curtailment of renewables. So wind farms, particularly in Scotland, because we are a net exporter, and we basically redline that grid connection to England, don't we? And I think there's more interconnects coming soon. But in the meantime, we can only export so much, and that means we're having to pay wind farms to shut down, isn't that right? So if we can,
it is. I mean, it's normal. Yeah, normal balancing. Yeah, absolutely. So I mean, this is the thing: is if you're paying a wind farm to stop, is one lens of balancing the grid. But if you know how much it costs to pay, generation to stop, what the avoided cost is to pay someone to put those electrons into a car, which is why, for me, the UK is really leading on this. So, the recent trials by some of the by some of the energy retailers to do that demand reduction, right? Can you use less? Now, that's not about sitting in the dark, with a candle, right, trying to read a book in the dark. It's just not adding to grid load. So those high intensive things in your home, like charging the car, running your dishwasher, running the iron, running the tumble dryer, just shifting that away. So actually you can create value and democratize energy. I mean, it's one of those things that becomes, so there's a couple of things we need to pick apart. So firstly, let's just go, because I see in the chat around V2G and V2X, we don't need, and I'm going to choose my words carefully, we don't need vehicle to grid until you get to about 80% of cars on the road being electric. Now, need and using is two very different things, right? We don't need to start pulling power out to help balance the grid until we get to about 80% penetration. That doesn't mean you don't want to do vehicle to grid, but there's also the piece here that smart charging, charging when it's clean and cheap and avoiding running when it's expensive and dirty, actually gets us a tremendous amount of the way there, which is why you often see the debate around vehicle to grid being either overhyped because you're into that, it's the only answer, or you find people shooting it down, saying it's not a thing because you don't need it till you get to about 80%. We need to have a rich debate around, just because you don't need it doesn't mean you won't use it. There's value extraction to be had elsewhere. So smart and connected is really important. But the UK is actually leading. The power system has always been run that power is turned up to meet demand and turned down to meet demand. What we can do now in the UK is you can democratize energy. So if you think about it, energy is done to you. You buy a house or rent a house, you register your meter, you get a bill at the end of the month. It's a page of numbers you don't understand, and you just have to pay it. By having time of use tariffs, smart charging your car, smart consumption, you are now a participant. Now, you can be a really geeky participant, and there are people on the chat rooms who are switching everything off. They're charging everything. They're running power leads to their neighbor, all those sort of bits and pieces to try and sort of gamify almost that participation. But actually, so much of this can just be for Mr. and Mrs. Bob and Jean average, just by the nature of a smart app, turning stuff on and off and just telling you how well you've done. So actually, everybody can democratize energy, whether you're an EV user or not, whether you're an early adopter or not, just by the nature of what we're doing. And because we know the cost of turning power up and the cost of turning power down, you know about that opportunity cost of what could you do for the money that, what could you have saved, right? What could you do on the demand side? Which is why you see some of those early trials. One of the recent ones, Octopus shed nearly 200 megawatts of power.
Whoa.
Now that actually avoided lighting the burners on a gas-fired power station.
That's incredible.
Right?
Yeah.
This is meaningful, tangible, and moving the dial. And actually the UK is we often think that we're just a little island and we follow the rest of the world. We're really pioneering in some of this sort of stuff, and the world is watching. And we're not the only people who are doing it, but the world is watching us. We're at the moment leading on that. And of course that then helps that democratization of energy. It helps you run energy intensives at the right time. It helps you locate energy intensives where the grid is cleanest and cheapest. And it's really fundamentally the way we engage with energy and the way networks and energy retail will respond to that.
So basically, in summary, there's a potential for significant carbon reduction and better utilization of renewables.
Well, I can give you some tangible numbers, right?
Yeah.
So I can give you some real numbers, Euan, just to dive in. So, earlier on I said, by 2050, we'll double the amount of electricity consumption. That'll mean 4 times the amount of clean generation. We'll need twice the grid. That's not my numbers. That's the Committee on Climate Change Balanced Pathway to Net Zero, right? The 6th carbon budget. So that's the legally binding stuff that gets us to net zero. But that is predicated, Euan, on really smart demand side management. That's also then predicated on really smart grid optimization. And that's also then predicated on really smart, accurate renewable energy forecasting 5 days out. Now, the cold reality is you won't get perfect demand side management. You won't get perfect grid optimization. You won't get perfect forecasting. So if you look at the National Grid future energy scenarios and their most green sort of scenario, it's the one that hits all of the legally binding targets. They broadly are saying we will consume about 3 times the amount of electricity by 2050, which means we need roughly 5 times the amount of clean generation, which means we need roughly 3 times the grid capacity. So this smart, agile, dynamic, utilization of consumption, actually there's a really, really important tangible value, not just on kilowatt hours into your car, cost to the grid, cost to UK PLC, cost of carbon. There's a huge lost opportunity cost there, which is realizable. And it's only when you see all of the options do you realize that everybody in the whole ecosystem has a role to play.
Definitely. That's incredibly insightful. We wouldn't have expected anything less from you, of course, Graeme, as someone who's been in the sector for so long. So just a quick heads up, there's a few questions coming in on the chat. If you can put them in the Q&A, please, we'll try and get to those as soon as possible. And one key thing that I would love to cover now, we'll come back to battery lifespan, but long story short, they're outperforming expectations. And actually, there are some studies from WMG that have shown that if vehicle to grid is done properly, can actually improve the lifespan of a vehicle battery, despite the fact it's being leisurely cycled a little bit more. But in terms of what happens to an EV battery when it dies, Basically, well, Emma, what does happen? Does it get landfilled? Does it get reused? Does it get recycled? What's the score? Because people seem to think they're ending up in landfill.
No, not necessarily. From the UK, typically it's the responsibilities of the OEMs to deal with what happens to the battery at the end of life. And we're, in a way, just reaching the first end of life from the first electric cars that were introduced, 10, 15 years ago now. So it's just started to kind of come into play. What do we need to do with all of these batteries that are reaching end of life, and what do we do with them? At the moment, the batteries are collected, and they are sent to, some of them are sent to recyclers. So some of them are sent to China for processing. In Europe, some of them are sent to Umicore, for example, for processing as well. And there's a couple of routes that people are looking at to recover some of the metals from these batteries. And we've already spoken about the value of those metals, cobalt and nickel being the highest value. And so these are prioritized in terms of their recovery, because you'll actually get something back for them. And so Umicore is an example of a pyrometallurgical recycling route. And what they do is they stick the entire kind of battery units, cells into a furnace. They burn them. They then produce a metal alloy and then a light fraction, which is also called a slag. And then in the metal alloy is contained the cobalt and the nickel and the high value components, which can then go in for hydrometallurgical processing. And then in the light fraction, you contain manganese and lithium. Now that manganese and lithium is basically waste. It's used to increase or decrease the setting time in concrete. So the lithium and the manganese aren't recovered from that process. The other thing with that process is that the plastics and the solvents that are in the cell are just used to generate heat during the process. So you just utilize them to produce energy. Lithium is also really volatile. It's a very, very light element, which means it's very volatile at high temperatures. And some of that also gets lost up with the flue gases. So we spoke about critical materials, lithium and graphite being two of those critical materials. If you use a pyrometallurgical route, neither of them are recovered. It's just the high value parts. We can use other routes to recovery. So hydrometallurgical routes, which are water-based, low temperature, you use acids to start leaching out the metal components of those batteries. This is also used after the pyrometallurgical route as well, it should be added. So to leach out the cobalt and the nickel from the metal alloy, you use hydrometallurgical routes to then leach those out, which is very similar to what you would use for primary ore extraction as well, which may link back to some of the work that Lucy's doing eventually as well in lithium recovery. So the hydrometallurgical routes, we typically do a shredding and sorting process. So we stick the batteries and the modules through a shredder. We then size fraction them, and then we can take off the plastics. We can take out the containers, the iron and the laminated pouch, and then we can start separating out the current collectors from that as well, until we're left with this black powder, which is known in the industry as a black mass. And now this black mass contains all of the interesting components that are in a battery, well, in my view anyway, the active material components, the graphites, the lithium iron phosphate, if we're using lithium iron phosphate, the transition metal oxides. And then we can use hydrometallurgical routes to start leaching out the transition metals and the lithium from those components as well, and then use extraction methods or solution-based extraction methods to then recover each of those salts independently to then remanufacture the materials to go back into a battery again, if we wish. So again, it's the high cost, valuable components that have been focused upon to date, the lithium, the cobalt and the nickel. lithium has not been necessarily a big focus because it's lower value than the other metals. However, if you look at the quantity of lithium, for example, in the black mass or even in the cathode materials, there is more lithium in the cathode materials than is in the lithium primary spodumene rock that you use to extract out lithium as a primary ore. So it kind of makes sense to me that we should be recovering lithium from these systems, because actually it contains quite a high content of lithium in comparison to some of the other sources that we're looking at primary sources. And because we're using similar methods for extraction to the mining industry, we may even be able to then partner up the recycling with the mining industry to then use the same processes for recovering those materials as well. And certainly if you look at some of the recyclers in China, this is exactly what they're doing. They're exporting some of the wastes of the battery to the primary processing sites to use the same methods for recovering some of those valuable metals and minerals and shipping them back all around the world. Obviously, we need to think more of a circular supply of our critical materials in the UK and Europe. So shipping them over to China or over to Belgium and then shipping them back again maybe is not the best use of our own mineral resources, especially not if we ship them over to China and then have to buy them back again, for example, which is sometimes what happens here. The other thing I think that that's interesting to talk about is the low value components, or we talk about lithium iron phosphate, which is a lower value component for a battery. Also, the sodium ion battery systems are a lower value, where some of these economics may not stack up for the recycling. And from a material scientist point of view, we put an awful lot of effort and design and engineering into our actual materials and our particles that we produce to put into a battery. I mean, they're very highly engineered, small spherical agglomerates of particles to maximize the transport properties in these materials for batteries. And then we just burn them or we leach all the metals out of them. So all of that really interesting material science and highly engineered particles that we've made, that they just kind of disappear. If we could do direct recycling, which is where we reclaim these highly engineered particles as they are, and then directly reuse them back into a battery again, then that would reduce some of the energy and the CO2 costs associated with recycling, and also the provide value to the materials that are potentially lower cost. So this would be true for the lithium iron phosphates if we could re-lithiate or recondition the particles to be able to directly reuse. And also gives opportunities for recycling sodium ion as well. So we also do some work on manufacturing and recycling of sodium ion materials. We can also do that for graphite. So we can directly reclaim graphite and reuse that back into a battery again. And if we're thinking now of reclaiming those materials, we can also go to the manufacturers and look at reclaiming those materials from their scrap that's produced in that process. I don't know how much scrap is produced. There's lots of numbers that go between about 2 and 20% scrappage in manufacturing, but that's an awful lot of materials waste. So if you can then reclaim those valuable active material components and put that back in at the beginning as well from the scrap from the manufacturing process, that would also help reduce waste and minimize that environmental impact too.
That is hugely insightful. Again, thank you very much, Emma. Shameless plug.
Euan,
Euan,
can I just add an additional one?
Yeah,
that was a brilliant answer, Emma. I've learned so much. But the other one for me, and bearing in mind, I'm not an electrochemist, this is not my specialist area. Actually, legislatively, when you make things in our part of the world, you actually have to certify where the things have come from, so guarantees of origin. So somebody made a comment here, Nigel Morris said, why aren't you thinking about second, third, sort of fourth life batteries? actually you might find that it's more valuable to put them into new batteries because of guarantees of origin than it is and scavenging, rather than actually, because you'll do as much as you can generate from, like Lucy's business, generate as much of that primary source, but you're going to have to supplement that with a certain amount due to help those guarantees of origin. So you might actually find that it's a legislative lever that speeds up the recycling rather than a risk to landfill. And it's one of those sort of strange external legislative, external economic drivers that often gets missed because we're so into the engineering and the science that we miss some of those externalities. So I just wanted to chuck that in the pot as well.
That's a fair point. Yeah.
I think that's an important point, because it's also about the battery passport, so the European battery passport that's being introduced, where a certain quantity of recycled content is going to be required by 2025, and then even more by 2030, and that includes lithium, cobalt and nickel, but interestingly nothing about lithium iron phosphate in there yet. So it'd be interesting to see what happens with the new cell chemistries, including the sodium ion systems, what the legislation actually states about that when they come into commercialization.
Great point about lithium iron phosphate not being on that list yet for the the passport requirements, because there's been recent news coverage about phosphorus extraction and the kind of environmental concerns there, which is something that's been used for fertilizer for ages, but because it's not been used in batteries until recently, the battery industry and the engineers and scientists around it have not been working on improved, more ethical extraction techniques that don't require tailings dams, etc. There have been some pollution issues in Florida because of phosphorus extraction, for example.
So,
but
the other point to make is phosphate rock itself, which is used as a primary source for fertilizer, is actually on the critical materials list as well.
Of course, yeah, good point.
Because it's really economically important, because we use it for fertilizer.
True. I suppose on the plus side, when we're using LFP in batteries, we're not sticking it in the ground, using it to grow crops, and then not returning the the phosphorus to the land. It's probably just ending up being effectively flushed out to sea and lost. And that was something that was discussed in that article. Actually, we're not closing the loop on that kind of circular food chain almost. But at least with batteries, that phosphorus is being retained and it can be recycled and used again and again and again. But I can guarantee you that as soon as the usual naysayers get a hold of that article, they'll say, oh, these batteries are bad too. But chances are, right across the board with the battery industry, as soon as someone has found a way to try and criticize EV batteries, someone is well on the way to commercializing a viable solution to that problem. Cornish Lithium is a prime example when it comes to lithium extraction. And it's only a matter of time before something similar for phosphate that deals with tailings dams, etc., is developed, because that intensely bright spotlight has been shone on its use in electric vehicles, which does not get shone on the use of materials in other applications, including petrol or diesel cars. So I suspect we'll be in a very good position in the not too distant future on the LFP side of things. And of course, sodium ion, lithium sulfur, there's all these chemistries coming along that move away from those materials too, to an extent. But yeah.
I was just going to add, and I think that raises a good point, because obviously we've identified that almost every material in the battery supply chain at some point has come under scrutiny. And obviously there are reasons. Often the oil lobby sponsors these articles and studies as a way to combat the adoption of electric vehicles, to slay the uptake. Without getting too conspiratorial, we see it in the press every day. And there will be a situation where we can't eliminate every single material from the battery supply chain out of the batteries. Some are necessary, and we will have to take a view on what is the least best solution in terms of picking the ones that are looking across the supply chain, identifying the environmental considerations across all of them. But there will still be some materials we use that aren't necessarily optimal from the absolute environmental point of view. But we will just have to look to optimize those processes, reduce the amount we use. I don't think we can constantly just move away until we'll just end up with no batteries whatsoever. You have to, at some point, acknowledge that not every part of the supply chain will be green, but we'll just have to work and improve on that as we can. Because I think there's a risk of constantly saying we'll go from lithium to sodium to something else, and then just infinitely move away, rather than acknowledging we will have to use LFP, we will have to use NMC, NCA for decades to come, and how do we make that as green as possible, rather than constantly looking to some future next technology that and there's a reason why chemically and performance-wise these chemistries aren't being adopted, because they are all suboptimal. We haven't got NCA and LFP by accident. We've got there because all these chemistries have been considered, and these are the ones the industry's chosen to put into energy storage and EVs.
You make a fair point. And as well, it seems that across the board, from raw material extraction through to recycling, the more ethical, less energy / carbon intensive or less polluting solutions are also the ones that are the most economically viable.
Yes.
In the case of direct lithium extraction, 3 times the yield with no freshwater use. Compare it to the oil and gas industry, where they seem to be doing everything they can. And this also goes for petrol and diesel. I mean, look at Dieselgate, look at NOx emissions, etc. They seem to be doing everything they can to avoid going down those ethical routes, because those actually cost more money. With batteries, it's flipped the whole situation on its head. Generally,
yep,
the ethical stuff results in higher yield and lower running costs, which means more money to be greener. And that is a significant thing that people who are used to petrol and diesel cars and the centuries worth of mindset that's been instilled around that will perhaps struggle to appreciate, and they'll initially think, nah, you're talking rubbish about this greener thing actually being better. It genuinely is, because it's a totally different ballgame. I'm aware that we have a hard stop in about 5 to 10 minutes time, and I'm aware that we're already 20 minutes over, but most of the audience are still hanging on, which is a testament to the absolute font of knowledge that all of you are in general and have been on this chat. So thank you so much for all of your insight. We should head to questions. Nigel rightly asks about, as Graeme pointed out, second, third, fourth life, etc. Just to point out, there are second life EV batteries in use at domestic scale and at commercial scale. And in fact, Dundee is home to a good example of that. There's some old Renault Kangoo electric van batteries stacked on top of one another in a shipping container at the city's biggest charging hub, which helped to power it off of excess solar power from the solar canopies. So there's things like that going on all the time, and second life batteries are also enjoying a healthy market for classic car retrofits, for example. Basically, as soon as someone gets a bit throttle happy and wraps their Tesla Model S around a tree, a fierce bidding war breaks out over the battery pack between the usual candidates in the UK who do these retrofits. But if we quickly head to Q&A, and again, thank you everyone for all of your incredible insight. Actually, yeah, some of you have been very busy answering all the questions. Thank you very much. There's a couple left open. So here's an interesting one. From Scott Bradley, is the move to structural type batteries less conducive to second use and repair of packs within the vehicle? So in other words, that second life application, what's our thoughts on that?
It is. So I've spoken to Chris from Zero EV. So they're one of the UK's main EV retrofits, and it is a problem, but we are already working on solutions to this. So at Amte, we're involved with a company called MEP Technologies, a Scottish-based vehicle integrator, and also yourself, of course, Euan, on a project called FlexiMod, where we were looking to develop a battery module that mirrored the modules that are already being used by these EV retrofitters. So effectively create a supply chain to replace the modules that will potentially fall out of the supply chain when there is a move across to structural packs. I would say it's obviously not the case yet that there will be more and more modules coming onto the market before it then diminishes. But with these things, you always have to plan ahead. So I think it's good that we've started some work in the UK on that already. But certainly, I've also worked personally, physically, on tearing battery packs apart, and it's amazing the difference between packs, for example, that you might see in an LEVC or Volvo product are very easy to disassemble versus something like a Tesla pack where there's a high amount of adhesive used. So that is, I would say, the key thing that makes it harder to take a large battery pack apart and redistribute the cells or modules into other vehicles or stationary storage applications. And that's also a point, is that chemistries are designed for the applications they're in. So it is preferable to put a EV chemistry back into an EV application, because that cell was designed to be run effectively with an accelerator pedal, be run as a power draw, wasn't designed necessarily to be run and cycled like in an energy storage or grid frequency application. They're quite different. So whilst they can be used, suboptimal. So ideally, you put these cells back into the closest thing to their original first life, rather than move away to something entirely different.
Very good point. Although on that note, I should point out that this teleconference is being powered today by my Nissan Leaf through Vehicle to Grid. So yeah, I mean, that said, yeah, I appreciate what you're saying about the energy storage side of things, but for vehicle to grid with EVs, at least it's not going to be harder on the battery because it's a much lower power draw and it's generally kind of more.
No, indeed.
But it's, yeah, I understand what you mean, particularly if you've got a situation in summer where you've got solar panels that are chucking out more energy than you need and it's just force feeding the vehicle to grid battery to keep the battery full. You want to be able to adjust it so that it's not topping it up completely and it's maybe letting that battery kind of slowly discharge a little bit. So, yeah,
I was talking more about larger scale rather than sort of domestic, where it's much more of a strain on the pack.
True. Oh yeah, exactly. When it's when it hits peak time on a grid frequency response battery or something, and it's like now, and it just there's that kind of side of things for sure. And that's where lithium iron phosphate is quite good because its ability to dump power quicker than something that, as you say, is designed for lower loads but longer range. So Dorothy,
Euan, there was another question. Actually, there was another great question because we were talking about frequency response and what have you. One of the previous questions I tried to answer was around where should you put batteries on the grid? Should you put them in homes? Should you put them in the distribution system? Should you put them in transmission? The answer is, let's not talk about battery storage. Can we talk about first flexibility? So with a highly renewable dominated grid, you'll have high highs and low lows. What you need is flexibility in all its forms. So flexibility can be demand side management, use less. We talked about Octopus. Flexibility can be shipping our power across interconnectors to another country. Their morning peak is an hour ahead of ours, right? So other forms of flexibility. We also need to think about batteries as one of those arms of flexibility. So this is not batteries cannibalizing batteries. This is other forms of flexibility having to be considered with batteries. And then the other piece is batteries are really, really good for frequency response and voltage control. They're not that good as a medium for shifting summer to winter, interseasonal. And therefore, what we need is the right flexibility mechanism, the right technology in the right location at the right time. And some of that can be done by batteries. And the answer is we need flexibility everywhere. So we've seen 50 megawatt batteries plugged into transmission. We've seen smaller stuff at distribution. You can be a participant in your home with a static battery, or it can be part of a vehicle to grid setup. So the answer is batteries everywhere, but don't think that battery in and of itself is some magic bullet to keep the grid stable. And you need flexibility in all its forms. So I wanted to just jot that in because it was part of an answer that was asked earlier.
That's a very, very good point. And it was also worth pointing out that there's energy storage beyond lithium ion, especially for grid storage, where you've got more room and that volumetric energy density is not as much of a concern. There's upcoming things like iron air batteries, which aren't very energy dense. They're quite big, but they can hold loads of charge for ages. Vanadium flow cells in general, cryogenic air. Look up what High View Power and Cheesecake Energy are up to. They're brilliant. In fact, Cheesecake Energy's compressor for the compressed air storage system is repurposed old diesel lorry engines that they have an electric motor on and they drive that and it works as a compressor. How clever
But also, Euan, we mustn't just think about this in the terms of electrons, right? So if you think of everybody listening, everyone on this call, their biggest demand in their home or workplace is not electricity, it's heat. So I personally use ground source heat pumps, but I use them only when the grid is cleanest and cheapest because I store that energy in the form of hot water. So I have large hot water tanks, and that means I can ride through those peak periods. So what we also need to think on is when people kind of do, what can I do at home or in my workplace? Don't leap to just installing a battery. Think about how are you using power? It's power to heat. So can you store energy in the form of another vector? So hot water, I mean, the difference for me was my heating engineer sized my water tanks to sort of 150, 200 litre tanks. And I said to him, how much to make it 300 litres? And he said, well, it's about 70 quid. Well, that means I can have 4 hours where I'm not drawing on the grid because of that additional capacity. So it's one of those things that when you're thinking about these things, don't often think about it's an electron that has to be an electron into storage and come back out as an electron. Think about some of the shift changing. You've mentioned some of the other technologies, but even in your own home, think about the storage mediums you already have before you think about additionality of home storage batteries.
True. I am acutely aware that we are about to run out of time, but there's two questions I want to very quickly answer. So one of them, which was asked in advance, was vehicle to load capable cars, ones that have like a 3-pin plug that you can run a lawnmower off the battery and things like that. Will there be a way to allow them to do vehicle to grid / vehicle to home and actually power an entire house? And without going into too much detail, I'm aware that there's a project that's received funding from a very talented British company, or for a very talented British company, to develop a means to develop vehicle to home / vehicle to grid out of vehicle to load capable vehicles. So if they have a 3-pin socket, then they could actually be modified to run your entire house. So that is coming, but can't give away too many details at this stage. And Dorothy has asked about living in the southwest of Skye and not being able to get a smart meter, so can't easily do smart charging. This is due to no or weak WAN, basically, the network coverage. And what would they need to do to get smart charging in their area? So, I mean, what first
I'm
thing
going to
is
do that one. Hang on, Euan. I live in the Thames Valley, 40 miles from London, and I can't have a smart meter because the walls of my house are too thick. So I work on a dumb economy 10 meter. So I do economy 10. So if you can't, there are ways of doing this as an interim step. The wide area network stuff will evolve. It will have to piggyback on GSM 5G in time. It'll have to piggyback on Wi-Fi in time. But one of the things from my perspective is, because I couldn't do smart metering in my home, I put an economy 10 tariff in, which means I'm using the cleanest and cheapest. It's not as smart. It's not smart at all, really, but it does mean you're accessing the cleanest and cheapest energy off peak.
That's a great shout. Actually,
it's not the right answer, but it's a step. It's an interim step.
That's really helpful. So we're basically going back to the days of storage heaters and that economy 7 / economy 10, but bringing it forward for EVs as an interim step. I hadn't thought of that, actually. But the other thing to add is, if you have a smart charge point at home, like an Indra Smart Pro or something like that, that's able to measure what your solar panels are up to, if you have solar panels, then you could already do smart charging during the day when the sun's shining, because it would take any excess solar power that your house isn't consuming, but your panels are producing, and put it into your car without drawing from the grid. So you effectively get free lecky in summer, and that's what happens with my setup at home as well. So obviously in winter, you've got to rely on the off-peak electricity tariff overnight to get the cheapest rates, but in summer, you're laughing your way to the bank. And on that note, we are out of time, unfortunately. There's been a huge amount of participation, a huge amount of attendance, particularly in this webinar, but right across the series. So again, thank you so much, Emma Kendrick, Fergal Harrington Beatty, Lucy Crane and Graeme Cooper. I shall leave it to Donald Monaghan from the FASTER project to round things out.
Thanks, Euan, and to all the panelists this morning. That was a hugely insightful session today. A lot of great information there. So hopefully everyone on the call found that really useful. I suppose just to give a quick update on where things are at with the FASTER project at the moment. We are just about to launch the public tender exercises in both Northern Ireland and the Republic of Ireland for the charging networks on both sides of the Irish border. So we would hope that those will be live now at the beginning of March. The documents, I believe, are just being finalised by legal teams, and then they'll go forward to the funder for the final sign-off. In Scotland, our colleagues at Hightrans are just in the final stages of the contract sign-off with the CPO there, and that announcement will be coming over the next week or two once I get the official go-ahead. As Euan has said, this marks the final webinar in the current series, but hopefully we will be back very shortly with a few more of the webinars. So do keep in touch via our social media channels and website for more information on the next series. If there are any topics which people would like to see discussed in those next webinars, do let us know, because we're always keen to have any suggestions and know what it is that you're interested in finding out more about. And so again, you can drop me an email or you can get in touch via the social media channels. And we'll also, in the follow-up email today, we'll perhaps include some information on that as well, as to how we can suggest some topics. Also, I suppose I want to say a big thank you to Euan for all his work over the course of the series, and to all the panelists that we've had on the calls over the past 10, 11 months. It's hugely appreciated. There's been a huge amount of knowledge and information shared, and I know that has been beneficial to so many organizations out there. So it's great to see that we had so many on the call today, and look forward to seeing you all again really soon. So thank you.
Thank you, everyone. Cheers.
Bye, everyone.
Bye now. Take care.